Hello everyone. So now we will be discussing about the next topic, that is gradient based learning. So what is gradient based learning? So in the gradient based learning, so what we see is we use a functions. So a function is a, we can say, a relation that has unique associate members of one set with members of another set. Okay, you can see that in this case, okay, the function which you can see here is f of x over here. So f of x is nothing but the the two parameters are involved, that is a and b, where two parameters can be, a can be the weights and b can be the intercepts, and x are nothing but the various inputs. So this relationship, this f of x is nothing but the relationships where you are mapping the various inputs, okay, this various inputs which is there, okay, with the outputs, that is output is nothing but f of x. So if I draw a graph, okay, so this is my x, this is my f of x. So to map my x with f of x, okay, I'm what is the function I'm going to use, what is the relationship? So where I'm using f of x is equal to ax plus b, where x is nothing but this input, a and b are nothing but the different parameters that are being used. Now in this case here a is nothing but equal to 6 and b is nothing but equal to 2. So in a linear function, okay, your output f of x is nothing but, okay, ax plus b, where a and b are nothing but the parameters and x is nothing but the input. Now coming to this, uh, if I'm if I'm taking this function, this output of f of x, okay, where a and b are nothing but the parameters and x is the input. So here if I draw a line, so consider my y is nothing but, we can say here parameter a is nothing but 2 and b is nothing but 4. So my equation now will be y is equal to, linear function will be y is equal to 2x plus 4. Now when I draw this line based on this linear function, so you get say that a is um, 2 and b is 4. So what you get is this. So here you can see that, okay, with my a is equal to 2, okay, and my intercept is nothing but equal to 4. This is my intercept, that is my, this is my y, okay, and this is my x, okay. Now with respect to x, okay, um my a is nothing but 2, okay, and with respect to y, my b is nothing but 4. Okay, so when I draw a line, okay, you get this particular uh but when I draw a line based on these 2 points, so we get this particular straight line. Okay, so here this is how you actually plot a graph with respect to, okay, when you are having a output function with intercept. So this is with intercepts, you get this, okay, and we express this as this 2, whatever is there, as is nothing but the slope of the slope of the linear prediction, okay, and this 4 is nothing but the intercept function. So intercept function, okay. So uh, so here 2x plus 4, here is nothing but 2 is nothing but the, nothing but the slope, and 4 is nothing but the intercept. Okay, now in this example we had seen that y is equal to, okay, this is nothing but out of the form of y is equal to ax plus b, okay, where a is nothing but your slope and b is nothing but the intercept, okay, and x is nothing but the input, okay, or you can say the input that is been given, okay, and with that you will be calculating the output y. Okay, y also can be expressed as f of a, okay, f of x of a, okay, which is nothing but equal to ax. Now what is this, is not, this is nothing but the the x is the here, which is nothing but x is the input function, okay, where a is the parameter of function. A is the parameter of function. So both actually mean the same. Okay, here you see that this is y is nothing but the output, which is respect to the slope that is added to the slope which is applied to x plus the b intercept. Now this is nothing but x is nothing but the input function, where a is nothing but the parameter of the function x. So here this also is a is nothing but parameter of with respect to x. This also you can say that this a is nothing but the parameter with respect to x, which is nothing but equal to ax. Okay. Now when we talk about the function, okay, in the machine learning, we often talk about the predictor functions. So there are different predictor functions or predictor map, you can say. So they are nothing but linear maps, decision trees. Okay, so it is a decision tree. Okay, logistic regressions, neural networks, and support vector machines. And also we talk about the loss function as linear root mean square loss. Okay, root mean square loss, hinge loss, logistic loss, and cross entropy. Okay, so these are the things which you have studied in your machine learning only. Okay, about different predictor function and also the loss and cost function and objective functions. Now coming to the linear predictors. Now your linear predictor in this with this there are one input. Okay, where we are considering only one input in consider, that is x as the input. Okay, at that point of time we take the output function. So f of x will be nothing but w integer, where w is nothing but your weight and x is nothing but the input feature. Whereas if there are multiple input feature, we represent it as x1, x2 up till xd. That means there are multiple dimensions of the inputs. Okay, so the function f of for that the function f of x is written as f of x1 up to xt, which is nothing but equal to w1 x1 plus w2 x2 up till wt xd. Okay, where you can see that f of x1 up to xd is nothing but the summation of the different weights and x. That is the summation of the different weights, okay, and the input x. Okay, summation of different weights and the different input x. And usually the input x1, which you can see here, is initially given as equal to 1. Okay, so some dummy feature is being added, so it's you need to introduce x1 as a dummy feature equal to 1. So if you use dummy feature, so your w1 x1 in this case, where x1 is nothing but equal to 1. Okay, so you get what you get is nothing but the bias. So what you obtain is nothing but the bias by applying your x1 is equal to 1. Now the same thing you could be expressed in different way for vector multiplication. So this is my vector multiplication over here. Okay, so in vector multiplication, so vector, okay, that is the of weight wt, okay, is having the shape of 1t. So that is nothing but the weight will be in the, this is nothing but the in the weight vector. Okay, so weight will be in the your weight vector, and the x, this is weight x, which is in the shape of d1. Okay, it's nothing but the for the feature vector. Okay, so now f of x is nothing but the w transpose x. Okay, where you can see that w is nothing but all the row vectors, for row vectors that is being used, okay, for the weights, and x1 to x2 is nothing but the column vectors that are used for the input features. So this is used for the weights, and column vectors are used for the input features. And after you multiply, so what you do is you actually multiply together. So that is weight transpose of x. Okay, we multiply together, you get the matrix multiplication. Okay, so sum of the matrix multiplication, what you get is the dot product between the, so broad product between the weights and the x input. Again, the weights and the x. So the sum of the dot product of the weights and the input is what you get it in the, okay, vector multiplication. So this is about the vector implementation. Next is the linear predictor. Okay, in the linear predictor, the predicted value y hat is nothing but, okay, hw of x, okay, is equal to w transpose x, which is nothing but the summation of the different weight and the input x. Okay, where x is nothing but your feature vector. Okay, w is nothing but the parameter, which is nothing but the parameter which is associated with x, which is nothing but the weight vector. Okay, which is nothing weight vector. Okay, and this is nothing but equal to, when we are applying multiple weights with respect to input, what we get is nothing but the hwx. Yh is, this is nothing but the um, the same thing is applied to the hidden units in the hidden layer. Okay, so the weights that are applied to the hidden nodes with the input x. Okay, okay, what you get is the predicted value y hat. Okay, so this is how your y hat is being calculated. Now, uh, to find out the best linear map, okay, you see that what we take is the prediction error. Okay, so here you can see that there are multiple um, linear equations. So y is equal to, okay, this is nothing but ax plus b form. So there are multiple such lines we are taking for prediction. So these are nothing but different prediction lines, which is in red, blue, and green. So these are nothing but your data. Okay, different data points you can see on in the black. They are nothing but different data for different data points. Okay, what do we do is we are actually performing the, okay, the prediction. What is the best prediction? Okay, we are going to, so by using a linear equation. Okay, how we are going to um, find out the best prediction. Now, what is that best prediction? Now you can see that if you're, okay, if you're for a data point, okay, if your y value, okay, so this is your the predicted value. Okay, so your true label value, this is nothing but the true label value. Okay, which is about y is equal to 5, and this is nothing but the, okay, the predicted value is -2. Okay, so you can see the difference between the true label value and the predicted value is, okay, there is an error between them. So there is an error between the true label. Okay, true label can be somewhat around 5, and this is around -2. So the difference between them is nothing but the, okay, the what is the loss function. Okay, so by using these linear functions, okay, we are supposed to reduce this what is that the prediction error. So how to do the how to reduce the prediction? Okay, that is what we actually do it in this case. So the equation for that is nothing but f of w is nothing but, now y1 is nothing but the true label and the prediction. Okay, so y1 minus y hat 1 whole square. So what we do is we are going to take the difference between the uh, true label and the predicted value. Okay, square root of it. So square root of the true label and the predicted value plus the square root of the true label and predicted label of the second uh, aspect. Okay, so like that, multiple such squaring, okay, we are going to find out. Okay, so after you perform the perform the multiple set square, to actually find out, take the mean of it, that is nothing but the 1 by m. So this mean, calculate the mean of the square root of the true value as well as the predicted value is nothing but your the loss function. Okay, is nothing but your loss function, and this is nothing but your f of w. The loss function is nothing f of w, and that is what you actually do it in this. Okay, so in this case, um, uh, that is to choose the best linear prediction. Okay, we need to, what we need to do is we need to use a mean square error loss to estimate the quality of the linear prediction. So this loss function minimizes the prediction error, and if the prediction is too large, which I just explained, okay, this is nothing but too large. Okay, so what we do is we actually square the prediction. Okay, and we find out the loss of the one which with having the minimum error. Okay, that is being found out. Okay, now how to find out the best linear map? So that is what we are going to do. So we can simplify our situation, where you can see, here you can see this is my x1 is nothing but the input. Okay, so under this we have one feature x of 1 and another true label is nothing but y of 1. So we have one feature, one, okay, and one weight, and we have certain linear predicted without intercepts, so they call coming to origin. So we need to choose the best linear, so best linear predictor. So these are the different linear predictors wherever, one is with red, one is with green, and one is with blue. So there are different linear predictor. So by changing so how can we do that is by changing the slope. So what is that slope? You can see that your this is the my loss function. So here you can say that we can try with the different values. So here you can see that, okay, this is my loss function where f of w is equal to y1 minus y hat whole square, which is nothing but y1 minus, if I expand this, okay, what I get is y1, okay, minus w1 x1 whole square. Okay, now so what we can do is um, we can try with different values of weights and see how it affects the gloss. So this is one weight. So initially I'll be having one weight. So my this particular weights are being, okay, changed, okay, in order to see that, okay, how it affects my loss function. Okay, so it and the to have so by doing so, the we get the better we'll be able to find out which one is the, okay, better prediction, and which one is nothing but the, okay, worst prediction, which one is the worst prediction. So what do we do is, okay, this is our function f of w, which I have shown in the previous slide. Okay, f of w is the mean of the true label and the predicted label. So f of w is nothing but for single aspect, which you can see for single prediction. Okay, what I'm saying, trying to do is the difference of the true label minus the predicted label whole square. The square of the true label and the predicted label is being done. Okay, and what we find out is the loss function. Now, this y hat one is nothing but is expanded as w1 x1. Okay, so y1 is minus w1 x1 whole square. So this is what, if we equate this y hat, we get this w1 x1. So where you can see that this w, which is nothing parameter, Okay, based on this, now if I want to find the best linear map, I have to change this parameter w. Now this parameter w, okay, is nothing but where we are changing the weights. Now by changing the weights, with different values, okay, we will be able to find out, okay, which is the best, okay, prediction and which one is the worst prediction, okay. And with that, okay, if you plot the uh, uh, plotted, actually we'll find out, okay, the where we are actually getting the best, okay, prediction. Now if we plot the loss function with respect to the weight, okay, so what we get is the the derivative of the squared error loss. So to calculate the loss, that is nothing but f of w is nothing but fy1 minus w1 x1 whole square. And as we had seen in the previous PPT, so in previous slide, that with the change in the weight, we will be able to find out the which one is the better algorithm. Now, in this case, you see that um, if you are having the losses, how does the loss function as how it is being calculated? So here you can see that one with the highest point, here you can see the loss function that are having the high values. So our main intention is we need to go down, okay, and get our loss function to the 0. So this fw of 0 equal to is nothing but the minimum of the function. So this bottom of the parabola, what we get is, okay, that is nothing but the minimum loss. Okay. Now same thing if we are applying the tangent over here. This is our tangent. Okay, in on the right hand side, you see that if we apply a tangent, you see that our the function, that is if I'm applying here, so uh, this is nothing but the function which uh, is greater than 0. So for this we need to find of the if I'm applying the tangent function, you see this is the meeting point. So the meeting point is of the tangent function, and the slope is over here. So when I'm applying the derivative of it. So what is a derivative? A derivative is nothing but a derivative function of a real variable. It measures the sensitivity to change of the function value with respect to change in its arguments in the input value. So in this case, if you see that, okay, the the um, the geometrical interpretation of the derivative is nothing but the slope of the tangent. So yes, here you see that, for example, if I choose the weight, okay, here my weight is nothing but equal to 10. My loss of function is nothing but f of w. Okay, so if I say it is somewhat over here. Okay, so at this is my point, because if I'm applying the tangent, okay, you see that it is meeting at this particular point. So you can see this is my time. Okay, my w is 10 and my slope of tangent f of w is also 10. Okay, now the tangent line means that it touches the loss function in one particular point. Now if the derivative here is positive, here you can see the derivative is in the positive direction. Okay, not in the negative, because it is going in this particular direction. If the derivative is in the positive, that is the change in the after change in the weight, my the derivative is in the positive direction. Okay, then function is actually growing. You see that there is a growth in the function. Okay, f of w. Okay, so if the derivative is in the negative direction, if I draw a tangent line over here, if it is in the negative direction, then the function will be, okay, f of w will be negative. Why it will be negative? Because it is your derivation is, okay, going in the opposite direction. So you can say that when it is somewhat if for understanding, let's see this one. Here you can see this is a complex graph. Okay, derivative complex function f of x is equal to x sine x square plus 1. Okay, now you can see that, okay, when I'm applying a tangent, okay, so with the you can see that if we are going from left to right. So once you're going left to right means we can say that there is a increase in the derivative. So the moment it is going upward, the derivative is positive. The moment it is going down means the derivative is negative. You can see that initially, okay, the derivative when it is coming down, the derivative is coming negative. When it is zero means okay, uh, it is nothing but there is no your f bar if the derivative is equal nothing but equal to zero. Now, moment it is going up, you can see that when the tangent is going up, you see that even the derivative is green, and now when it is going down the slope, it is nothing but the negative. Okay, so this is what you can see. Okay, where you can see the tangent when it moves. Okay, towards the right, and if it is moving upward, okay, right and upward, that means your the derivative is positive. If it is going in the downward direction, okay, right and downward direction, then your derivative is nothing but your negative. Okay, that is what I just now told. So in this case, if it is going in the, so even though here you see that this in this it is going in the right hand side, but it is going downwards. When it is going downwards, that it means that the derivative here is negative. Now, if it is in this case, if it is going that is when you are applying tangent, and if you're with this, okay, you can say that the derivative is positive because the next data point is okay towards the towards this direction. When the next data point is towards this direction, then you can say that okay the derivative is okay, positive. Okay, now, but in the case of gradient descent, okay, the things are a bit different. So what we are going to do in gradient descent is if you are having the weight wk, okay. So in gradient descent, what we find out is what is the minimum cost. So for that, for finding a minimum cost, we need to change the weight. You can see that I have changed the weight from W of k to W of k plus 1. Now with the change in the weight from W of k to Wk plus 1, okay, we can see that I am moving towards the minimum, that is the minimum cost. Okay, so so uh, this is what we are actually going to do. So this is a slope red in red for a slope that is not a slope, that is a quadratic equation, that is nothing but the red line. Okay, if initially it is over here, and this is nothing but wk. Now I have changed my weight, okay, to go towards the minimum cost, which is nothing but wk plus 1, and as a result you can see that it is coming near to the minimum cost over here, which is, so this is my minimum cost. Okay, so when the so this is the one when your function is uh, positive in your function, that is derivative function positive, you see that it is going in this direction. Okay, when my derivative function is negative, it will be going in this particular direction. Okay, that is from left to right it will go. So if there is somewhat here, if I want to change my way to go towards minimum cost, it will go from okay left to right, this direction it will go. Or else if my derivative is positive, it will go from right to left. Okay, to sum it up, okay, the derived of squared error loss, okay, you need to know is nothing but your f of w, okay, is nothing but the difference of, that is the square of uh, the labeled output, okay, or you can say the output, actual output with the predicted output is being done. So this is my predicted output. So square of the predicted output, say labeled output and actual output. Okay, the difference of the label of the actual output is being calculated, and we are squaring that. That is how we are actually performing the f of w. Okay, or else we when if I expand this, okay, we'll get it as w1x. So to better our to in order to have the improved function, okay, what we do is we actually improve linear function. We what we do is we actually weights change the weights, okay, according to, okay, accordingly, so that we get the improved results, okay, that is we'll get the minimum cost, okay. Now, how we are going to perform derivation? So there are different derivation rules here. So you can just go through this derivation rules. Okay, you can pause the video and you can just see the derivation rules how we are going to perform. And see, the f of x is equal to cx is equal to if you are deriving that with respect to x, what you get is c. F of x is x square. If you are deriving that is equal to 2x. So this is nothing but how we are performing the derivation. So cx is nothing but with respect to x is nothing but c. Now x square is with respect to x is nothing but 2x. So what we are going to perform is nothing but the chain rule, which you can see over here. Okay. So to summarize the in gradient descent, okay, for a particular data point m is equal to 1, and the one input feature x of 1 and one weight w of 1. So we are actually performing predictor as hw of x is nothing but w1 x1. So we are multiplying the weight with the input, okay, feature x. And how we are calculating the loss? We are calculating loss by f of w is equal to y of 1 minus y hat of 1 whole square. So square root uh, of the uh, actual output minus the predicted output. So this is how we are actually calculating the loss, okay, and this is how we are calculating the, okay, we are performing the prediction. So this is the equation for predictor, and this is the equation for the loss. So what we are going to do in gradient descent is we are going to compute the prediction given the current way. So that is what for y hat, okay, what we are going to do, we are going to whatever for the different weights that is applied to the input x, okay, okay, based on that, okay, we'll be seeing the output, we'll be getting the predicted output, okay. So that is what compute prediction with given the current weight, then compute derivation of the loss function. So this is the loss function, okay, that is f bar of w is nothing but minus 2x1 y hat minus y hat minus 1. So this is nothing but after applying the mean of loss for uh, uh, multiple losses. So you'll get this particular value, and then the updation of the weight. Okay, so updation of weight is equal to wk plus 1 is equal to wk minus alpha fw of k. So where alpha is nothing but your learning rate, alpha is nothing but your learning rate, w of k is nothing but the new weight, okay, or I guess the previous weight is nothing but the previous weight, and if this is nothing but the new weight, okay, this is nothing but your new weight, okay, and this f bar of wk is nothing but the change in, okay, that is nothing but your gradient descent, okay, change in weight, that is nothing but gradient descent, okay. So if you are applying the gradient of multivariate function, okay, this is how we are going to calculate the change in the weights. So this is nothing but change in the weight, okay, with respect to the function f of w, okay, that is nothing but with w1 w2 up till w3. So this is for multivariate function, this is the equation that we are finding out. And to find out the gradient descent, okay, what we do is the the, the new guess, that is wk plus 1 is nothing but the current guess, that is the uh, what is the previously what you have guessed about the weight, okay, which is nothing minus the learning rate alpha and the gradient descent. Okay, so this is how we are going to calculate the gradient descent if you are going, okay, in the downhill direction. So if this is the to find out the minimum cost function, okay, you actually what you do is initially it will be wk, next it will be wk plus 1. Okay, so this is my wk, so then it is wk plus 1. Okay, and to go from year to year, okay, I am using alpha as the learning rate, and also to go from wk to wk plus 1, okay, I am applying a gradient descent. Okay, I apply a gradient descent which is nothing but delta f w of k. This is what we can say the gradient step that is being used. So the gradient step, the delta f of k is nothing but the mean of the uh, what x of 5 y minus change w of k transpose x of 5. So this is actually about the gradient step. Okay, and then next thing is about stochastic gradient descent. So in gradient descent, what we are seeing, okay, this is my uh, how we are going to perform the gradient descent. That is the equation which you have seen. Whereas in the this is nothing but my gradient estimate for the stochastic gradient descent. So stochastic gradient descent is nothing but unlike in the normal gradient descent, you have the uh, the complete data set that is being applied. Whereas in stochastic, you will be using the batch wise. So that is nothing but the subset. It is nothing but the subset of the gradient descent that is being used. So if you can see it in stochastic data gradient descent for a data set m is equal to 50. Okay, we have batches s equal to 10. Okay, so we are splitting the data set into, okay, multiple batches, that is 10 10 10 10 10. And you can see that each uh, batch of data set 10 is applied. Okay, and it's nothing but the applied and it's nothing but the iteration 1 2 3 4 5. So when we're uh, when it is a first iteration, during the first iteration, we are taking the data set of size 10. Okay, in the second iteration, we are taking the data set of size 10. Like that, for 5 iteration, we are taking data set of 5 10. Now, for this data set, for each iteration, what we are going to do is we are going to compute the gradient descent. So initially, if it is like this, initially with data set of size 10, okay, we are applying the gradient descent. Then you'll go to the next uh, batch, okay, where the data set is of size 10. Okay, so with that, we are what we are getting is the updated weight also here w1, and for second iteration the weight is also different w2. Okay, like that we keep on applying the different weights for different iteration. Now all these 5 iteration together, okay, all these 5 iteration together, okay, will make one, okay, one epoch. One will make one epoch. Okay, so that is what you can see in the table. Okay, so data size of size 50. Okay, where you can see there are 5 iterations, that is I think 5 batches, okay, of size 10 each. Okay, and put together, okay, it will be one epoch. So that is nothing but 5 iterations are there. Now same way, if we say data size is of size 50 with batch size 10, and if there are 10 such epochs, so you can say this is one epoch, so I'm applying 10 times your epochs are given. So total number of iterations are nothing but the 5 into 10, which is nothing but 50. Okay, so 50 iterations are there. Same way, if the number of epochs are 20, my number of iterations will be 200. Okay, so this is your, okay, what the gradient descent. So if there is any query, please let me know. Thank you.